Hello, I'm Alex Sanchez, and today we're going to talk about the 2D hydraulic equations implemented in HEC-RAS. Hydraulic modeling is a multidisciplinary field concerned with fluid flow and hydraulic behavior. As a hydraulic modeling software, HEC-RAS is involved with aspects of other areas such as fluid mechanics, data processing, and engineering. This presentation will cover the conceptual framework of HEC-RAS, emphasizing hydrodynamic concepts like mass and momentum balance, friction, and turbulence. Computational concepts, including the mesh, numerical methods, and subgrid bathymetry, will also be covered in detail. I'll start by going over some basic principles such as mass and momentum conservation, which give us the shallow water equations. Then I'll talk about the specific terms in the momentum equation. I'll explain how to derive the diffusion-wave equation, and at the end I'll go over some of the numerical methods used to solve the equations in HEC-RAS. The most important principle we want to enforce is mass conservation. By assuming constant water density, the mass conservation can be written in terms of water volume. And this equation is referred to as the continuity equation. It basically means that within a control volume, the change in water volume is balanced by the flows coming in and out. The bottom equation is a simple finite volume discretization of the continuity equation. This is the momentum conservation, or simply momentum, equation solved by HEC-RAS. I'll describe each term in detail in the following slides, but very quickly they are from left to right: the temporal term, advection, Coriolis, pressure gradient, momentum diffusion, bottom friction, and wind stresses. The equations are basically Newton's second law written here with the acceleration on the left and the forces on the right. Obviously, the equation is depth averaged, but also it has some assumptions like constant water density, hydrostatic pressure, and others. The momentum equation is nonlinear and a function of both velocity and water level, so it's coupled to the continuity equation. The system of continuity and momentum equations is the shallow water equations. In HEC-RAS, they are sometimes referred to as the momentum equations. HEC-RAS has two solvers for the shallow water equations: Eulerian and Eulerian-Lagrangian. They differ in how they treat the acceleration terms. In the Eulerian approach, the frame of reference is fixed in space and time. It's easier to compute, but it's limited in the time step due to the Courant condition. In the Lagrangian approach to the acceleration terms, the frame of reference moves along a flow path. It's more expensive to compute, but it allows for larger time steps. The Coriolis acceleration is a result of the Earth's rotation. It conserves angular momentum within the rotating reference frame of the Earth. It's the reason why storms spin counterclockwise in the northern hemisphere and vice versa in the southern hemisphere. The Coriolis parameter is a function of latitude, but HEC-RAS models are small enough that an average latitude can be used to compute a constant Coriolis parameter for each 2D area. This is known as an F-plane approximation. Coriolis is disabled by default, and for most river and flood simulations, the Coriolis effect is negligible. However, it can be important for large domains or higher latitudes. Hydrostatic pressure assumes the vertical water accelerations are small compared to gravity, and this is true for most RAS applications. The total pressure is the sum of the atmospheric pressure and the weight of the fluid above a point. Since atmospheric pressure is assumed constant in RAS, the horizontal pressure gradient only includes the gradient of the water surface. Diffusion of momentum is caused by turbulent mixing and dispersion. RAS has two formulations for the diffusion term, also known as the mixing term. The non-conservative formulation was the only option in versions 507 and earlier, and is still an option in 6.0. It computes the Laplacian of the velocity field times the eddy viscosity. For many natural flows, the Laplacian tends to be on average negative, and this results in a net dissipation, which is not good because it can start to increase water levels upstream, and in order to calibrate, the bottom roughness has to be adjusted to compensate. This is why a new conservative formulation has been developed. It's the default version in 6.0 and is the only option with the Eulerian shallow water equation solver. It computes the divergence of the diffusive fluxes, and for this reason it's more conservative. This slide shows a comparison of the two mixing term formulations for a simple parabolic channel. The top plot shows the bathymetry and the water level. The middle plot shows the velocity with the non-conservative formulation in black. The blue line represents the velocity profile without mixing. Because the velocity curvature is negative everywhere, the mixing term results in a net dissipation and lower velocities. The bottom plot shows the velocity with the conservative formulation also in black, and with the blue line representing the velocity without mixing for comparison. There, the velocities are decreased along the center of the channel and increased along the sides, which is a much more realistic result. Another thing that changed in 6.0 is how the eddy viscosity is computed, or the turbulence model. In versions 5.07 and earlier, the eddy viscosity was computed with a simple isotropic parabolic model. It has one parameter, the mixing coefficient d. In versions 6.0, there is a new turbulence model which has a non-isotropic mixing coefficient and an additional Smogrinsky term, which is a function of the horizontal velocity gradients. This is important because areas with high horizontal shears produce more turbulence. The new turbulence model is better, but it's more computationally expensive. It also has 3 parameters instead of 1. These are the longitudinal and transverse mixing coefficients and the Smogrinsky coefficient. If the longitudinal and transverse mixing coefficients are set to the same value and the Smogrinsky coefficient is set to 0, it reduces to the previous turbulence model. Bottom friction is the resisting force due to the relative motion of the fluid against the bed. The nonlinear bottom friction coefficient in the momentum equation is computed as a function of the Manning's roughness coefficient, gravity, the velocity magnitude, and the hydraulic radius. Wind forcing is a new feature in 6.0. The wind surface stress is computed as a function of the atmospheric density, a drag coefficient, and the 10-meter wind velocity. Several options are available to compute the wind drag coefficient. There is also an option to choose between Eulerian and Lagrangian reference frames. The Lagrangian reference frame takes into account the relative motion between the air and water, whereas the Eulerian reference frame ignores the water velocity. In general, it is always recommended to use the Lagrangian reference frame because it's more physically accurate and stable. Now that we have gone over all the terms in the momentum equation, let's see what happens if we ignore all of them except the bottom friction and the water level gradient. If we do that, we get a simple momentum equation shown at the top. It can be manipulated mathematically to obtain an equation for the velocity. Then inserting the velocity equation into the continuity equation leads to the diffusion-wave equation, where the beta is the diffusion coefficient. What's very convenient about this equation is that it no longer is a function of the current velocities. It only has water levels. Therefore, velocities can be computed once a solution for the water surface is obtained. The diffusion-wave equation is simpler and more computationally efficient to solve compared to the shallow water equations. However, the diffusion-wave equation has a more limited applicability than the shallow water equations because we are ignoring a lot of terms. There are some general guidelines for when to use diffusion-wave or shallow water equations, but because it's so easy to switch from diffusion-wave to shallow water equations and RAS is so fast, the best practice is to try them both and compare. I always recommend starting a project with diffusion-wave because it's faster and more stable. Then once the model is running well, try shallow water equations and compare. This is the most objective and evidence-based way of knowing. HEC-RAS uses an unstructured polygonal mesh. The polygons or cells consist of sides or faces connected by face points, or better known as nodes or vertices. Cells can have up to 8 faces. Cells must be concave. Multiple 2D meshes can be run together or independently. Each cell has a computation point which may or may not be the same as the cell centroid. In version 6.0, the computation point is only used for mesh generation and editing, and is not used in the model computations. Instead, the cell centroid is used in the computations. Both the diffusion-wave and shallow water solvers are semi-implicit. This is because terms are treated as explicit, semi-implicit, or fully implicit. By treating the fast pressure gradient term implicitly, the time step limitation based on the wave celerity can be removed. Also, both diffusion-wave and shallow water equations are solved with finite difference and finite volume methods. Time integration is finite difference, the continuity equation is finite volume, and the momentum equation is finite difference. There's no control volume for the momentum equation. The phase water surface gradient calculation has changed in version 6.0. The change is small, and in fact, for Cartesian cells, the schemes are identical. But for other cells, they can vary, and for highly distorted meshes, they can vary significantly. The gradient is computed with a simple two-point stencil. The approach uses the orthogonal distance between cell centroids and not the distance between computation points, as before, and there is no correction for non-orthogonality. We may include corrections in the future as an option, but the new two-point stencil is efficient and robust. We're also going to be working on mesh quality to improve the model accuracy. Because momentum conservation is directionally invariant, we can simplify things and only solve the momentum equation in the direction that is needed, and that is the face normal direction. The tangential velocities could be solved with a momentum equation just like the face normal velocities. However, it is much more efficient to reconstruct them from the face normal velocities. The phase tangential velocities are computed with what we call the double C stencil approach. The method computes two phase tangential velocities, one on each side of a face. A full velocity vector is reconstructed on the blue and red C stencils shown in the figure by solving a least squares problem. The face normal component is then thrown out because it's already known, and the tangential component is applied at the face. If the two cells are hydraulically connected, the average phase tangential velocity is computed as a simple average of the left and right tangential velocities. The same double C stencil approach is used to compute the phase tangential water surface gradient utilized by the diffusion-wave equation. The cell velocity gradients are computed by applying the divergence theorem and are needed for turbulence modeling. The cell velocity vector is computed with Perot's method and is needed for the conservative form of the mixing term and for advection in the Eulerian shallow water equation solver. The Laplacian of the velocity field is computed on the nodes based on the cell velocity gradients. The image on the right shows the mesh and dual mesh. The blue circles are the nodes and the red X's are the neighboring computation points at which the velocity gradients are computed. The Laplacian is computed similar to the velocity gradients by utilizing the divergence theorem, but in this case on the dual mesh shown in red. As mentioned previously, the Cronk condition is avoided in the Eulerian Lagrangian solver by incorporating advection in the total derivative. An integral part of this is backtracking, which is the process of tracing back the flow path or characteristic line from a face to its starting location x at the beginning of the time step. The algorithm in RAS is computationally efficient, robust, and has good time step convergence. The actual algorithm in RAS is more complicated than this because of boundary conditions and special cases, but this is the general idea. First, the node velocities are interpolated from the faces using the previous time step velocity field. The backtracking starts at the faces. The starting location A is set to the face center F, and the remaining backtracking time T sub r is initialized as the time step. Next, the location B is computed from the starting location A. Then the time to location B, T sub B, is computed. Then the velocity at B is interpolated from the nodes. If T sub B is greater than the remaining time, the particle has crossed into a neighboring cell, and B is set to the new starting location, and T sub B is subtracted from the remaining time. If T sub B is less than the remaining time, the particle is within the current cell. In this case, the location of x is computed as shown. The velocity of x is interpolated from the velocities at A and B. And finally, the face normal advective velocity is computed as the dot product of the face unit vector and v sub x. In the ELM shallow water equation solver, the Coriolis term is treated semi-implicitly as shown in the first equation. As in previous slides, the subscript x indicates the backtracking location. Theta is the implicit weighting factor. In order to implement this within the solver, a fractional step method is needed consisting of two steps. The first step includes only Coriolis and computes an intermediate velocity, u and v star. The second step includes all the other remaining terms. The second fractional step of the ELM solver is shown here in semi-discrete form. The velocity Velocity un star is the face normal component of the intermediate velocity computed from the first fractional step at the backtracking location, and therefore includes Coriolis. The water surface gradient is computed semi-implicitly based on the weighting factor theta. The mixing or diffusion term is explicit and Lagrangian. In other words, it's interpolated at the backtracking location x and is based on the previous velocity field. Lastly, the friction is treated semi-implicitly. The semi-discrete Eulerian momentum equation looks similar to the Eulerian Lagrangian equation. As before, the water surface gradient and friction are semi-implicit. However, the Coriolis term is treated explicitly. There's no fractional step method here. The mixing term is also explicit and Eulerian. The main difference between the ELM and EM solvers is how they treat advection. In the EM solver, advection is computed with what I would call a finite volume advection interpolation approach. It reminds me of the Ryan-Chow momentum interpolation approach. Basically, advection is computed on either side of the face and then interpolated onto the face. Here the alphas are the interpolation weights. A simple first order upwind scheme is used to compute the advective velocities. The non-conservative form of the mixing term is only available with the ELM solver. It's computed as the explicit face eddy viscosity times the dot product of the velocity Laplacian at the face and the face unit vector. The velocity Laplacian is interpolated at the backtracking location x. The eddy viscosity could also be backtracked, but tests have shown that it's more stable to use the face value of the eddy viscosity. The conservative form of the mixing term is available with both the ELM and EM solvers. It's computed with a similar weighting scheme as the Eulerian advection, but here the divergence of the diffusive fluxes are summed around the left and right cell faces to compute a diffusion term on each side. Then these are weighted to compute a face value of the diffusion term with the same alpha coefficients as the advection term. In order to simplify the code, the same discretization is used for both the ELM and EM solvers. However, the ELM solver uses the mixing term backtracked to the location x. This removes the stability criteria from the diffusion term and allows it to use a larger time step. Comparing the Eulerian Lagrangian and Eulerian shallow water equation solvers, the ELM solver was the only one available in 507 and earlier. It's the default solver in 6.0 for various reasons. It's not limited by the Courant condition, it has excellent stability, but it can have momentum conservation problems around shocks or where the flow changes rapidly. The EM solver is new in 6.0 as an option. Its Courant number is limited to less than 1, but it has very good stability and improved momentum conservation for all conditions. The table on the right shows a comparison of different strengths, features, and capabilities for the two solvers. Water levels usually vary much more smoothly than the terrain, and it's unfeasible to resolve every detail of the terrain with the computational mesh. Therefore, the approach of the subgrid modeling is to utilize a grid resolution sufficient to resolve the hydraulics and capture the details of the subgrid terrain through hydraulic property tables. This slide shows how the subgrid bathymetry works at a cell. On the left, you have a cell that is partially wet and dry, the blue region being the area underwater. The terrain is bent into discrete elevations which can be used to create a curve of horizontal area as a function of elevation, shown in the middle. Each bin represents the area corresponding to specific elevations and is used to compute the total wetted cell area for a specific water level. The area elevation curve is integrated to produce a piecewise linear volume elevation curve, shown on the right. This curve is used to compute the cell water volume for any water level. The subgrid bathymetry at faces is computed similar to cells. The property tables computed at faces are the wetted length, wetted perimeter, and wetted vertical area. The figure on the left is an example of an irregular bed profile at a face. The light blue shaded region is the wetted area corresponding to a particular water level. The figure on the right represents the relationship for the face area and the water level for that face. Shown here is an example of how the computational cells in HEC-RAS contain enough hydraulic detail that flow can move through a channel even though the channel is smaller than the cell size. In the example, the cells are 500 by 500 feet. Water will move through the channel portion of the cells because the details of the channel cross-sections are contained within the faces. Additionally, the details of the cell elevation volume curve allows for accurate water storage within the channels. In this type of example, flow can move through a cell or channel in a 1D type of mode, while flow in the overbank areas will be 2D from cell to cell. If the user wants more detail within the channel, such as 2D flow velocities and varying water surface elevations, then smaller cell sizes can be easily specified within the channel. However, if the goal is to convey water through the channel and capture the 2D flow in the floodplain, this is a very good option. The solution procedure goes as follows. For both the diffusion wave and shallow water equations, the discrete form of the phase normal momentum equation is inserted into the continuity equation to obtain a nonlinear and implicit equation for water levels. For example, in the case of the diffusion wave model, it looks like the first equation. The subscript n plus theta indicates the implicit weighting, where the theta is the implicit weighting factor. Because the cell water volumes are a function of the water level, the equation is solved iteratively. Once the water levels are obtained, the new time-step phase normal velocities are computed with the discrete form of the momentum equation. The final system of equations can be written in matrix form as the first equation. The computational algorithm begins each time step by computing the right-hand side, which contains the sources and sinks and explicit terms. The outer loop computes or updates the linearized terms and variables such as the coefficient matrix and wetted surface area. The inner loop ensures mass conservation and computes water levels via Newton-like iterations, which require solving the sparse matrix problem shown at the bottom. Both the inner and outer loops are repeated until convergence. The 2D model supports various types of boundary conditions. A stage hydrograph can be specified upstream or downstream. Water can flow in and out of a stage boundary, and there can even be flow reversals within the same boundary. Flow hydrographs can be specified upstream or downstream, but are typically specified upstream. The flow hydrograph requires a user-specified energy grade slope, which is used to compute a normal depth from the flow rate and the bathymetry profile on the boundary. A conveyance approach is then used to distribute the total flow at the boundary along every face. A normal depth boundary condition can be used only at downstream boundaries and requires a friction slope. The rating curve boundary condition specifies the total boundary flow as a function of stage. It can only be specified at downstream boundaries. The total flow is then distributed along the boundary based on conveyance. Wind forcing is new to version 6.0. Wind stresses are computed based on the wind velocity data and can only be applied with the shallow water equations. Precipitation, evapotranspiration, and infiltration are also new to 6.0. These are applied as sources and sinks within the continuity equation. 1D reaches and 2D areas can be connected or coupled together. Multiple 2D areas can also be coupled together, and finally, 2D areas can be connected to 1D lateral structures, such as levees. And with that, thank you for watching. For HEC-RAS downloads, documentation, and other things, please visit the HEC-RAS website shown here. The latest online documentation can be found on the Confluence website shown here.